Okay, so here we are starting with the concept of the chapter ray optics. This is called as the lens maker equation. In order to understand this equation, first we need a particular equation which we derived earlier, and that gives you the relation between the image distance, object distance, the radius of curvature, and the refractive indexes. That is mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon r. Okay, we are going to apply this equation in this particular theorem so that we can get the perfect lens maker equation. Now let's understand what is there in this lens maker equation. It is nothing but a refraction which is happening through a thick convex lens. Okay, so this is our convex lens, and this is the refractive index of the outer medium, we can say air medium. This is the refractive index of the glass, and this is the refractive index of the another outer medium, air medium. Okay, there is a light object which is at O. We all know that the object, when it is incidented in a straight line, it moves in a straight path and it doesn't get refracted, so it doesn't get bent when it is incidented in a straight line. Then when we incident it at a particular angle, it bends inside that particular medium, and then again after coming out, it again causes refraction. Okay, so now there is a double refraction which is taking place. First refraction is happening at the surface A of the lens, and the second refraction is happening at the surface B of the lens. Okay, for each refraction we are going to use this particular equation, and we are going to frame this. Now what happens here is that the object O, okay, the ray OA, which is called as the incident ray, okay, as it reaches this surface A of this particular lens, okay, for this surface at this point A considers O as the object, and it forms the image. It bends this light and it tends to form the image at this particular point, which is called as I dash. If B was not to be there, then the A could have formed the image directly at I dash. Okay, so for A the image is at I dash, and for A the object is at O. But what happens as the ray passes on, it strikes another surface B. Okay, now for B the object is not this O. For B the object is the image which A was going to make, that is the I dash. So for B the object becomes I dash, and that object B bends it and makes an image at I. So there is double refraction which is taking place. First refraction happens at A, second refraction happens at B. Okay, so let's see how the distances are being distributed. Here object to the lens is called object distance denoted by U. Here the image to the lens, this is image distance denoted by V, and here this is the first image which was to be formed by this point A, that is I dash we have taken, and this is nothing but V dash. Okay, so we will apply for each refraction. For first refraction we'll apply this equation. What the equation says is mu2 upon V minus mu1 upon U is equals to mu2 minus mu1 upon R. Okay, so mu2 is the same. This is the particular equation when the light is passing from first refractive index 1 to refractive index 2. Similarly here also the same thing is happening. For first refraction it is passing from mu1 to mu2, so we can take mu2 and mu1 as their own places. Okay, even the mu2 minus mu1 will be on their own places. Now the V is the image distance. Okay, so for this point at O, point at A, the image is formed at I dash. The refracting surface A forms its image at I dash. It was going to form the image at I dash, so the image distance will become V dash. Okay, so instead of V we can write V dash, and U1 is nothing but U, so that is nothing but U, that is the object distance, it doesn't change. R, so there are two radius of curvatures here. For this side we will take it as R1, for this side we will take it as R2. So here we are taking the first refraction, we can take it R1. Okay, now for the second refraction, again we are going to write the equation, but this time the light is passing, but this time the refraction is happening at this point B. Okay, where the light is going to pass from the lens to the inside in the air medium. So it is passing from mu2 to mu1. Okay, here it was from mu1 to mu2, here it will be from mu2 to mu1. So all the cases will change. Here instead of mu2 will get mu1, instead of mu1 will get mu2, and this will be mu1 minus mu2. Okay, so first we'll write down the refractive indexes. It will be mu1 minus mu2, which will be mu1 minus mu2. Okay, upon. Now the next part is the image, that is V. Okay, now V is not changed because for this point B it forms the image at point I, and that is V, it remains the same as it is. But U is the object distance. Now for this point B, it doesn't take this O as its object, it takes this I dash as its object. So the I dash ka object is given by V dash. So here the object distance becomes V dash. So this is V dash upon R1. This was the first radius of curvature for the first lens, half of the lens, and the half of the lens we take it as R2. So this is the equation number 1 and this is the equation number 2. Now all we are going to do is we are going to add these two equations. Okay, so adding both the equations, what we get is we'll add this part and then this part. So we should get something like this. This is mu2 upon V dash minus mu1 upon U plus mu1 upon V minus mu2 upon V dash, which is equals to mu2 minus mu1 upon R1 plus mu1 minus mu2 upon R2. Here the two common things are this mu2 V dash, mu2 D plus mu2 V dash minus mu2 V dash. Those will get cancelled, and all we get is mu1 upon V, this part, minus mu1 upon U, which is equals to, now again if we change the, if we want to keep these two parts common, then we need to keep them in the same order. So that's why I shift this mu2 outside, take this mu1 minus, take a minus common, and then it will be minus inside. So it will turn out like this. It will be mu2 minus mu1 upon R1, and that will be plus it will be again a minus mu2 minus mu1 upon R2. Okay, so if you just take it inside again, you will have the same case here. Okay, now your minus goes inside, it becomes plus, and your mu2 is again minus. Now if you take both of them common and mu1 common from here, you will get 1 upon V minus 1 upon U, and here you will get mu2 minus mu1, and inside you will get 1 upon R1 minus 1 upon R2. Okay, again you take this mu1 downwards, then you get is 1 upon V minus 1 upon U is equals to mu2 minus mu1 upon U1 mu1 into 1 upon R1 minus 1 upon R2. Again this 1 upon V minus 1 upon U is nothing but 1 upon F. That is the mirror equation, which lens equation which we have. So that is why what we do is 1 upon F is equals to mu2 minus mu1 upon mu1 into bracket 1 upon R1 minus 1 upon R2. Okay, in order to make it more simpler, we can take 1 upon F is equals to, this is mu2 upon mu1 minus 1 into bracket 1 upon R1 minus 1 upon R2. This is the final equation called as the lens maker equation. Okay, when all the things we take into consideration while making lenses are the radius of the curvature of the lenses and the refractive index to get the focal length of a perfect focal length. Okay, so in the chapter semiconductor, we are going to see the transistor in action. That is the transistor in the input and the output characteristics of a transistor. Okay, so let's see. There are two types of transistors basically, which we have to what we study is only the one type. There are NPN and there is PNP. So the one we are studying is an NPN transistor. Okay, so let's first draw the diagram of a transistor. So a transistor, just generally it looks like this. Okay, it has got three parts. So there is this smaller part, again a smaller part, and a bigger part. Okay, so because this is an NPN transistor, so the N means this is the negatively charged electrons which are present here. Again here the negatively charged electrons are there which are present here, and the positively charged protons are there. Obviously, as you can see, the region for the protons is less and the region for the electrons is more on both the sides. Okay, so now giving the supply to this transistor, how does this? But first we need to know a few things. That this is the emitter part of the transistor, this is the base part, and this is the collector part of the transistor. The collector current, whatever we are going to get, we are going to get it from this side. Okay, now let's put the connections on. This transistor is going to run into two types, once in a forward bias and then again in a reverse biasing. So in the forward biasing, it is like the emitter and the base, firstly we are going to forward bias both of them. So the emitter and the base, we forward bias them. Now what do you mean by forward biasing? We connect the negative with the negative terminal, positive with the positive terminal of the battery. So here this goes the positive and here it goes the negative. Okay, so when this is done, we again think about the other part. Now here the emitter and the collector are connected, so they are again connected like this. Okay, so this is the emitter and this is the collector of the circuit, which is again this is a positive and this is a negative part. Okay, so this is again reverse bias and this is again forward bias. Okay, so the current, firstly what we are going to supply is this particular cycle which is going to work. So let's start the circuit. Okay, now what happens here is, as we switch on the circuit, the negative current, the negative electron starts moving inside, and then they make a place there because they get attracted towards the positively holes. They move here and the holes, they again move towards the positive. Okay, so here there is a cycle which is being completed. Okay, so the amount of electrons which will enter inside this particular wire, it will depend on the amount of holes here. The larger the number of holes, the more the number of electrons will come and they'll go out. This is the forward biasing. Now this is the way we give the input to the particular transistor. So the input characteristics are the same. Here between the negatively charged between the negative electrons and between the positive holes, there is a barrier in between. We all know that this is the potential barrier which is there, and to break this potential barrier we need a voltage of about 0.7. so obviously the current won't move forward until the voltage reaches about 0.7 volts. Okay, so the characteristics we can write it like this. Okay, this is your current, this is your current, this is your voltage. Okay, so the voltage here can be 0, 0.1, 0.2, 0.3, and here might be something 0.7. so your current won't increase up till the value 0.7. as it increases, as it reaches further above 0.6 or 0.7, the current will start reaching its peak. Okay, so this is a normal forward biasing diode. Okay, forward bias diode, when we give it a forward biasing to this particular end. Now let's talk about the reverse biasing. Okay, reverse biasing is the actual case where we are going to get a higher gains from this particular collector part of the transistor. So what we do is we again connect a negative terminal to this electron and positive terminal here. So the holes are getting transferred here and the negative electrons are getting transferred inside. So here the content of the negative electrons is more, and that content is again been brought forward because of this positively charged holes, and again this barrier gets broken down and the electrons again they move forward here and they get collected. A large number of electrons get collected in this part, which we can remove out, which we can get as their output current. Okay, now the main thing which acts to get your output current is the number of holes here. If you increase the number of holes, for each value of the number of holes, the electrons which are getting transmitted on this part will increase. Okay, so if you want to get the output if you want to get your current output to be maximum, then you increase the number of holes. The base current should be the maximum. Okay, but if you keep your base current up to a certain limit, then you will get increase in the collector current, but that will become stagnant after a certain period of time. Okay, you won't get any further increase until and unless you increase the base current more further. Okay, so your output current will be, output characteristics we can say, will be something like this. You will get a graph like this. Okay, and this graph will be again the same thing. It will be your voltage with respect to the current. Okay, but here we are applying the voltage from the base to the emitter. So this is your base emitter voltage, and the current which you are going to get is from the base only, so it is your base current. Okay, and here the voltage which you are applied is across the collector and the emitter. So this is your collector emitter voltage, and the current which you are going to get is from the collector, so it is the collector current. Okay, so the value of collector in the milliamps, it can go from 0 to 2, we can take it 4, you can take it 6, you can take it 8, you can take it 10. Okay, and your current the voltage across the collector and emitter, obviously it will be 1, 2, 3, 4. Obviously there is a band, there is a particular barrier here which needs to be broken, so it has to go further. We are showing it above 0.7. okay, so when the voltage starts, if you suppose the value of IB first, Okay, the first value of IB, suppose you have kept is 10 microammeters. So that for that particular value of IB, your volt current will raise. Your current, you will get an increase in the current, but that increase in the current will become constant and your voltage will go on increasing. Okay, but again, if you increase the value of IB further, if you keep your IB as 20 microamps, okay, so for that 20 microamps, again your current will increase further, but again it will become constant. Okay, so for each and every value of your base current, your current will go on increasing and increasing, but it will become constant after a particular amount of time. Okay, so this is your output characteristics for voltage across the collector emitter and the voltage the current which you are getting from the collector. Okay, in this way we can use your transistor as an amplifier. We are getting a larger currents here, current from this part, so as a result we can amplify whatever signal we are getting, we can get it amplified from this particular part of the transistor. Okay. Now in this chapter electromagnetic induction, we are going to study the concept of alternating circuit with a resistor in its end. So this is an alternating circuit with a resistance, and the voltage across it is given by the equation E, which is equals to E0 sine omega t. Okay, now we suppose that now we are going to find out what is the current, what is the change in the current and the voltage with respect to the when it is passed through this resistance inside an AC circuit. Okay, so here what we have given is the voltage equation which is supplied to this circuit, which is given by E equals to E0 sine omega t. Now according to the Ohm's law, what we get, that voltage is equals to current into resistance, so E can be equals to I into R. Okay, and similarly you can write I is equals to E upon R, but here E, the voltage is given by this equation, so here I becomes equals to E0 sine omega t upon R. Okay, now for your current to be maximum, that is for I becomes equals to I naught, that is the maximum amount of current, your E0 sine omega t, your sine omega t has to be the 1, so that means your angle should be 90, so sine 90 will become 1, and hence what will remain is E0 upon R. So at your maximum I naught, you get E naught upon R, because sine omega t becomes equals to 1. If you put this in the equation, what you get is I becomes equals to I naught sine omega t. Now this you can just take a look at this particular equations, and you take a look at this particular equations, you can take that here, you can write this I naught is equals to E naught upon R, as a result of which your I will become I naught sine omega t. That means your current will become your I naught maximum when sine becomes how much, 90. Similar way we showed it here. That means your the equation for your voltage is E equals to E0 sine omega t, and for your current is I equals to I0 sine omega t, right? So if we draw a graph of this particular thing, the flow of the current and the voltage through this particular is when it is an alternating current, so obviously the current has to be, it is the I which is going like this, it is reaching its maximum, again coming down, going to the alternating part of it, and then it is moving out. Okay, so this has to be your I naught, which is nothing but the peak of your current, and this is your I, which is nothing, which is starting at point t equals to 0 at your angle, which is here, which will be pi by 2, 90. At 90 sine omega t will become 1, and hence you will get a maximum value for the current. Okay, same way happens with the voltage, but the voltage is having at a slight peak is slight with the greater amplitude it works, but it runs in the same way as the current is, because both of them there is no phase difference in their angles. So we can draw the voltage as like this, it will be having a greater amplitude and it will move in the same phase as that of the current, and this particular part is the peak value of your voltage, which will be again 90 degree. At 90 degree it will be E0, so here if you use 90 degree as sine 90, it will become 1, so your E value will reach to E0 and your I value will reach to I0. Okay, so this is the relation between the voltage and the current when the alternating current is passed through a resistor. Okay, now the another concept when the AC alternating current is passed through a inductor. Now there is an we can consider that an EMF E is applied across this pure inductor, okay, inductor coil. With this inductor coil, obviously it is having a self inductance L, okay, and we are passing a current which is given by the equation I, which is equals to I0 sine omega t. Now due to the self inductance, an EMF is generated, a self EMF is induced by this particular coil, okay, and this is the back EMF we say. Now there is an E which we are producing, and there is a self inductance which is produced by this coil, which is given by minus L di by dt, okay, and this will be the total EMF inside the circuit, which will be equals to 0. So if you solve this, you get E is equals to minus L di by dt, which is nothing but equals to 0. So E becomes equals to L di by dt, okay. Now in this particular equation, E equals to L di by dt, if we substitute the value of I, which is equals to I0 sine omega t, we get L d by dt, it is nothing but I0 sine omega t. Now in this, we are differentiating this equation with respect to sine, so the omega factor will come out. It will become E is equals to omega L I naught cos omega t. Now this is your equation for your EMF E, which has been there, and if that E, voltage, if it has to reach the maximum value, then your cos omega t has to become 1, okay. So if this cos omega t reaches 1, then what you get is E will become E max, which is called as E naught, and that will be omega L I naught, okay. Now if you change this put this particular equation in here, we get E will be equals to E0 cos omega t, where E will be E0, E will reach the maximum value when your cos omega t will become equal to 1. In terms of sin theta, we can write this E, which is equals to E0 sin omega t plus pi by 2, okay. The reason we write in sin omega t plus pi by 2, sin omega t plus pi by 2, we get the two equations, one for the current here and one for the voltage here. So if we write the two equations simultaneously, the current when an inductor is connected is I equals to I0 sin omega t, and the voltage is given by E is equals to E0 sin omega t plus pi by 2. Now from these two equations, we come to know that the EMF, whatever it is leading by a phase difference of pi by 2, and the current, whatever it is lagging by a phase difference of pi by 2, and both of them, the EMF and the current, both are the sinusoidal, okay, and they are of the same frequency. So if you draw a graph of this, it is an alternating current. First we'll draw the graph of a current which has been normal out here, which is lagging obviously, so we can write the normal current out here. So this is the current, okay. Now to show that the EMF is leading by pi by 2, we have to start from here, okay. So here it comes down directly like this, it reaches here, it goes here, comes this part, and then again it moves forward like this, okay. So this is your current, which will be again at maximum I0 when the angle will be 90. So this is your 90 part, okay. When your current is at 90, when your current is at 0, your voltage E, obviously it is at 90, it is leading, so it has already reached 90, it has already reached its peak value, and it will reach its peak value when it is equals to E0, that is this part will become 1, okay. So this is your current, which is given by the equation I equals to I0 sin omega t, and this is your voltage, which is given by the equation E is equals to E0 sin omega t plus pi by 2. So now here the voltage is leading and the current is lagging by a phase difference of pi by 2 when it is connected to an alternating current, when it is connected to an inductor passed to a alternating current, okay. The next concept is the alternating current when it is to a capacitor, okay. So this is a capacitor connected to an EMF which is alternating E. The equation for the EMF is given by E is equals to E0 sin omega t. Now this is a capacitor, so the capacitor is going to store some charge, and the potential difference across the plates of the capacitor is given by the formula V is equals to charge upon the capacity of the capacitance, okay, where this V can also be written as in terms of the applied EMF E, which is equals to Q upon C. Now your Q ka equation becomes E into C, okay. Now this is your E, which is the applied EMF, that is E equals to E0 sin omega t. So if we keep it in that terms, then you will see E0 sin omega t. Differentiating the charge with respect to time, this will be charge with respect to time. So this will be dq by dt C E naught sin omega t. Now when you differentiate this equation, it gets the charge upon time is nothing but the current what we get, and that current is equals to the omega part will come out omega c e naught, sorry, omega c e naught sine, sorry, the cos will, sine will become cos, right? So your current I will become omega c e naught cos omega t. Okay, now again in this particular part your current is I, so that I will become maximum, that will become I naught, when your cos omega t will become 1, and what will be remaining is omega c e naught. Again you can put it in this equation, the equation for the current will become I, which is equals to I naught cos omega t. Okay, so I becomes equals to I naught cos omega t. Again the cos factor, if you need to change it into current, into sine, we get I equals to I naught sine omega t plus pi by 2. Hence we get two equations, one for the EMF which is applied E, which is equals to E0 sine omega t, and for the current I, which is equals to I0 sine omega t plus pi by 2. Now here in these two cases the current is leading the EMF E by a phase difference of pi by 2, or else you can say that the voltage E, the EMF E is lagging the current by a phase difference of pi by 2. Both the currents and the voltages here, both the current and the EMF here are showing a sinusoidal wave, and they are having the same frequency. Okay, so if you draw a diagram of this alternating current, so here we have a voltage which is moving normally as a sinusoidal wave, so this is the voltage which is moving normally, and there is a current which is leading by a phase difference of pi by 2. So obviously it is leading, so it should start from here, go here, then it has to go from here and again here. So this is your E, which is equals to E0 sine omega t. It will reach to E0, that is at this point when your angle will become pi by 2, and this is your current I, which is equals to I0 sine omega t plus pi by 2. That is already at the peak. When the voltage is starting, your I is at pi by 2, it is already at leading by an angle of pi by 2. Okay, so this is how you understand when a capacitor, when an alternating current is passed through a capacitor, the current is leading and the voltage is lagging by a phase difference of pi by 2. The next concept is from the chapter electrostatics. It is the energy density of a medium. Now what happens is, whenever we charge a conductor, the work has to be done to bring some charge on the surface of the conductor. Okay, so this work is stored in the form of electrostatic energy, and that electrostatic energy per unit volume is called as the energy density. Getting me? So if we suppose that electrostatic energy is given by U, per unit volume will give you the energy density of that particular medium. Getting me? Now next, for this we suppose that we have the force, we have the formula for the mechanical force per unit area of a charged conductor. So the mechanical force acting on a charged conductor is given by F, which is equals to half epsilon naught E square. Now if that force is to be acted on a particular area ds, then the equation becomes F is equals to half epsilon naught E square ds. Okay, now in this particular case, now we imagine that there is a surface area ds which has been pushed outwards through making a distance dl. This is the distance dl. Okay, so there is a surface area ds which is pushed outwards. Okay, and the distance covered is distance dl. Okay, now what we are supposed to do is, we are going to restore this element back to its original position by applying force F. Okay, therefore the elements, they move slowly back through this distance dl. Okay, now whatever the work we are supposed to do when we move this particular surface ds back to its original position, that work is given by the formula dw, and work is nothing but force into displacement, and the displacement we are going to cover is F into dl. Okay, now your F is having this formula, which is the mechanical force, because whatever force is required to move this out, the same force will be required to move it out down. So this will be dw, which is equals to half epsilon naught E square ds dot dl. This is ds dot dl, that is the surface area into the length, that will give you the volume. Okay, so this becomes your half epsilon naught E dv, and this is your dw. Now whatever the work we are going to do here, it is stored in the form of electrostatic energy. So you can change this work factor by the energy factor du, and that becomes half epsilon naught e square dv, and this particular energy with respect to the volume upon the volume will give you the energy density. So if you take du upon dv, you get the equation half epsilon e square. Okay, so this is nothing but this is the energy stored per unit volume or the energy density of the particular medium. Okay, here the energy density is nothing but the energy stored per unit volume, and that is what the equation we are getting, energy density, that is energy stored per unit volume, given by half epsilon naught e square. Okay, so the next concept is mechanical force acting on unit area of a charged conductor. So what is the mechanical force which has been given, which is acting on a particular area by a conductor which is charged. Okay, so for that what we have is we have a conductor, and on that conductor we have 2 points, which is point A and point B. This point A is just near the surface and outside the charged conductor, and point B is just near the surface and inside the charged conductor. Okay, and this is the area which is ds, the surface area. Also there is the electric fields which are acting. Even and this even electric fields are the electric fields which are due to the charge ds. Okay, on this charge ds, whatever the electric fields are, they are given by this E1 and this E1, so they are acting both outwards and inwards. Okay, whereas E2 are the electric fields due to the charge on the remaining area of the conductor. So whatever the remaining area of the conductor is, that is the E2, which are only acting outwards. Okay, now what we consider is, we consider a positively charged conductor which is kept in a medium of permittivity epsilon naught. Okay, and it is having a ds, which a surface area ds or on that particular conductor, and the density, charge density of that area is sigma. Okay, now the electric field intensity at this point A is given by what? So the electric field intensity E at point A is given by E, which is equals to sigma upon epsilon. Okay, but this electric field intensity E is nothing but the addition of all the electric field intensities at the outside. Okay, so that is nothing but E is equals to E1 plus E2. So that is what we get, E1 plus E2 is equals to sigma upon epsilon. Okay, now this component of the E1 and this component of E1, they are both opposite, they are directed opposite to each other, whereas the components E2 and E2, they are directed equal in the same direction to each other. Okay, so as this E1 and E2, they are directed opposite to each other, so therefore for this point B, the resultant intensity E will be E1 minus E2, because one is going this way and the other is going this way. For B, one is going this way and the other is going this way, so the resultant magnitude will be E1 minus E2, as a result of which that will become 0, so that will be no electric charge will be there inside this particular conductor. So as inside this particular conductor E1, the total electric field E is nothing but E1 minus E2, because it is this way, one is one showing, both of them are having opposite directions, so the total is E1 minus E2, which is becoming equals to 0. So you can get E1 is equals to E2, right? So you can take either E1 or E2 in this particular equation. So we take E2, so what we get, instead of E1 we take E2, which is equals to plus E2 equals to sigma upon epsilon. So E2 plus E2 becomes 2E2, which is equals to sigma upon epsilon. So E2 becomes equals to sigma upon 2 epsilon. Okay, so this is your value for the electric field intensity on the remaining area of that particular conductor. We took the electric field intensity at the point A also and at the point B also, and from both of them what we got is the electric field intensity at the remaining area. Now we are supposed to find out the force which is acting by this on that particular area by the charge conductor. Okay, and that force is the mechanical force which is given by the charge on the selected area ds multiplied by the electric field intensity on the remaining area. Okay, so the force is given by the charge on ds. The charge on the ds is nothing but sigma ds. Okay, because q becomes equals to sigma into ds into the electric field intensity on the remaining area is sigma upon 2 epsilon. Okay, so what we get is sigma into sigma becomes sigma square ds upon 2 epsilon is your force. Now we are supposed to find out the force acting per unit area, so that is the force upon your area is ds, that becomes equals to sigma square upon 2 epsilon. Okay, this f upon ds entire we'll take it as a small f, which is equals to sigma square upon 2 epsilon. Okay, now for this sigma square, what we have the equation is E is equals to sigma upon epsilon. So if E is equals to sigma upon epsilon, then sigma becomes equals to epsilon naught E, right? So if you place this here, you get the force is equals to epsilon naught E square upon 2 epsilon, right? So the epsilon goes on, and what you get is equals to half epsilon E square. This is the force per unit area acting on a charge conductor, of a charge conductor acting on a certain area. Okay, this is the mechanical force which has been given out by a charge conductor over a unit area, that is given by half epsilon E square. Now this is the next concept of the chapter current electricity, Kirchhoff's law. So Kirchhoff has two laws. The first law is a network connection. So what the law says that the sum of all the algebraic currents at any junction is always equals to 0. So whatever the currents are moving away from the 0 and away from the center, or they are moving towards the center, the sum of all of them will give you the value of 0. Now what you do is, we take the currents which are flowing towards the junction as positive, and the currents which are going away from the junction are negative. So here if we have take I1, it is moving away, it becomes minus. The same way I2, it is moving away, it has become minus. Again I3 is moving towards, it becomes plus. I4 is moving towards, it becomes plus. And again I5 is moving towards, it becomes plus. That is nothing but equals to 0. If you simplify this, it becomes I3 plus I4 plus I5 is nothing equals to I1 plus I2. So this is the Kirchhoff's first law. This is called as the current law. Okay, the sum of all the currents at any junction is equals to 0. Okay, so next, this is the Kirchhoff's law, or this is called as the Kirchhoff's second law, also called as the voltage law. Okay, what the law states that while tracing a particular circuit, if we travel in the same direction as that of the direction of the current, then the voltage is negative, otherwise it is positive. And when we travel in the same from the negative to the positive side of a cell, okay, then your EMF, whatever you'll get across the circuit, it will be positive, otherwise it is negative. Okay, if you move from the negative to the positive of a cell, then your EMF will be positive, otherwise it will be negative. Okay, so these two laws we are using in this particular circuit, and we will try to make the equations which for the particular loop, okay, to understand this thing better. Now we'll take 3 loops here. So first loop is nothing, this is the loop number 1, and that loop is A, C, D, F, A. Okay, so this is your A, C, D, F, A. So we start from A to C. Now before going forward, we will look how the current flows inside the circuit. What are the currents? So here there is a current, always moves from positive to the negative terminal of the cell. So it moves from the positive, goes down, moves here, up, down, and then it goes back. Okay, so this is the positively moving current, which is I1. This is current is I1 here, it is also I1 here, it is I1 here, and again here it is I1. But for the another cell E1, E2, the current is moving in this way, positive to negative. So it goes here, it moves up, it goes in this particular direction, again comes down, moves up, and this way. So the current here is I2, and the current which is going in this particular resistance here, there are 2 currents going, so it will be I1 plus I2. Okay, again the current here is I2. Now we find the current in this loop A, C, D, F, A. Okay, so a voltage in this loop A, C, D, F, A. Now we move from A to C first. We see that against A to C there are 2 resistances, that is R2. So the current across voltage is given by current into resistance. The current here is I1, and the resistance is R2, right? We are going in the same direction as the current is going, so it will be minus. Again we come down, we get another resistance R4, and we get another current I2. Now we are going in the opposite direction as the current is going, so we get it plus. Okay, next we move forward, we move from A to C. Now we are moving from C to D, we move to E2. Okay, so we get E2. Now in E2 we are going from positive to negative, Here they say negative to positive, it is positive. So we are going other way around, so it will become negative. Okay, so again we move forward, we get R5. R5, this is the resistance with the current I2. Again we are moving in the same, in the opposite direction as where the current is current wants to go, so this will become again positive. Next we move up, D2F, nothing is there. Again we have another resistance R1. This R1 is having a current I1, and that is in the same direction as the current is going, so it will be minus. Okay, again we come to E1. Okay, and then E1 we are moving from negative to positive, that is negative to positive, it is positive, so E1 will become positive, entire thing equals to 0. So this is your particular equation which you are going to make for a particular circuit. Okay, this is a bigger loop. Now if we take a smaller loop, like for loop A, B, E, F, A. Okay, so for this loop, one second. Okay, for this loop A, B, E, F, A. Now we go from A to B. Again we get R2, and the current we are getting here is I1. We are going in the same direction as the current is going, so we get minus here. Okay, next we move from B to E. We get R3, and we got two currents, I1 plus I2, right? But here we are moving in the same direction as the current, so this will also become minus. Again we move from E to F, nothing, and then F to, again here we get a resistance R1 with the current I1. It is in the same direction as the current is going, so it will become minus, and there is an EMF E, that is E1. We move from negative to positive, so this will become positive, which is equals to 0. Okay, same way you can do it with the loop, the next loop, that is loop B, C, D, E, B. Okay, B, C, D, E, B. Now we try to go from B to C. Okay, so from B to C we see that there is R4 and R2, R4 and I2, right? They are in the different opposite direction than the current, so they will become positive. Next we move to E2. E2 is positive to negative, so this will become negative. Next we move to R5 and I2. R5 and I2, they are again in the opposite direction as the direction of the current, so this will become positive. We move from D to E, nothing. E to B, we move from E to B, we get R3, I1 plus I2. This is in the opposite direction as the direction of the current, so this will become positive, which is equals to 0. This is the way you are going to